So question number 6. Okay, so for this question, we're asked a rectangular storage container with an open top is to have a volume of 8 cubic meters. The length of its base is twice the width. Material from the base costs $4.50 per square meter. The material for sides is $6 per square meter. Find the cost of the material for the cheapest such container. And we're given an image. We'll open this up. So this is just the question again. So let's just close that. So let's go through what the junior tutor said. Here the surface area has to be optimized. So this is an optimization question. While the volume is kept constant, length is 2 times the breadth. The breadth is x, and so on. So now they have kind of missing words in between this. So this isn't really a full solution. And it doesn't look like they give the correct answer at the end. So we'll go through step by step how to obtain the correct answer for this problem. So this is question number 6. So the first thing we want to do is just kind of write down some givens. So we know that the volume will be 8 meters cubed. So we have 8 cubic meters. We can draw kind of the picture of what this box looks like. So we have some box as such. So something like this with, let's say we have here the length of its base is twice the width. So if we have L over here and W over here, and we have H over here, and we know that there's an open top, so there's no material in the top area. So this area there's no material, it's just open. And then material for the base costs $4.50 per square meter. So we can say for base is $4.50. And for sides, I believe for the sides, we'll represent that by S, is $6. So 6. Find the cost of material for the cheapest. So we're trying to look for the minimum. We're trying to find some function and look for the minimum. So we know we can start off by saying volume. So the volume of this container would just be length, width. So length times width times height. And then the next thing that we can define is based on this statement. The length of its base is twice the width. So if we did 2 times the width, we'd end up with the length. So we could say length is equals to 2W. And we'll substitute this into this equation. So we'll say this would give us the volume, which we know is 8 from above. This is given in the question, which will equal L, which we know is 2W, times W, the width, times the height. This will be 8 equals 2W squared times height. We'll isolate this for height, so we know height is equal to 4 divided by W squared. Okay. So we'll keep this in mind. So let me just erase some stuff to make some space. So we've figured out how to derive this. And we'll erase this. Okay. I'm going to take this and move it up here because it will be useful to us later. Okay, the next thing we want to do is define a cost function. So let's say cost, we'll represent that by C, will be equal to 450. We know that's the cost for the base. 450 times the area of the base. So we represented the area of the base with L and W from our diagram. So we'll redraw the diagram again. So we had something like this. And like that. We had W and L and then H. So we have LW. So that's all we need. We know that the top is open. And then we add the 6 for all the sides. So we need an equation to represent the area of all the sides. So we'd have 2WH plus 2LH. So this side and the back side is represented by WH times 2 because there's two sides, and then this side and the back side of that, or the opposite side, is L times H, which gives us 2LH because there's two sides of that. So this is our cost equation. Now we're going to substitute in some things that we already know. We know this and we know this. So we're going to substitute H and L to get all this equation into the format where C is represented by W, which is the width of this box. So the variable W. So we'll say C at W will equal 450 times 2W, so that's for L, times W plus 6, and then we have in brackets 2W, so W you'll say the same, H, which is up here, 4 divided by W squared, 4 divided by W squared, plus 2L, which is 2W, 2W times H, which is 4 divided by W squared, in brackets. So we'll keep going with this. So we have 450 times 2, which is 9, W times W, which is W squared, and then we have plus. So we have the 6 in front. We'll keep that in front for a second here, and we'll look at inside the bracket. So we have 2 times 4, this is 8. And then we have W divided by W squared, which is just divided by W. And then we have 2 times 2 times 4. So 2 times 2 is 4. 4 times 4 is 16. So we have 16. And then similarly, W divided by W squared. So we have divided by W. And this will give us 9W squared plus, so 6 times 8. So 8 plus 8 is 16. 16 times 2 is 32. And then adding 16 again to that, we would end up with 48. So for the first one, we have 48 divided by W. And then 6 times 16, so 6 times 16, we end up with 96. So actually we can add these two together. So 96 plus 48 gives us 144. So we'll erase that. And we'll write it all together as 144. Oh, whoops. That didn't work as I intended. 144. And that is our cost function. So from here we want to take the derivative. We can also write this as follows. So we're going to take this bottom out and we're going to write it in this format so we can make the derivative easier. So we'll erase some space up top. So really, we only really care about the final equation. Okay. So this is CW. So we take the derivative of this function, and we set that derivative to 0 to find any maximums or minimums. So the derivative of the function below is 18. One second. So 18 w plus, so this is actually -1 over here. I erased that accidentally. So we'd have actually not plus, so we'd actually have minus. So we have minus 144 w to -2. So setting this to 0, we'd have 18 w minus 144 over w squared. This would give us 144 on the left side divided by w squared, which would give us equal to 18w. So we'll divide both sides by 18 and we'll multiply both sides by w squared. So we'll end up with 144 divided by 18 is equal to w cubed. Therefore we know that the cube root of 144 over 8. So I wonder if this divides out visibly. Yep, so this is 18. So 144 divided by 18. 144 divided by 18 is 8, sorry. So yes, and then we get w is equal to 2. So we know 2 times 2 times 2 will give us 8. So 2 times 2 is 4, times 2 is 8. So the cubed root of, so we'd have this, and the cubed root of 8 would just be 2. So we know that the width is 2. So we'll just double check that math. Yep, that's correct. And now we can take the second derivative and plug in 2 to verify that this is a minimum. So the second derivative of this function is 18 minus plus, 288 w to the -3. And if we plugged in 2, so if we set the the second derivative of that function and we sub in 2, we would end up with 18 plus 288 divided by the cubed root of 2, and this would be a positive value. So the actual value is 246, but all we really need to care about is that this value is positive. So this is greater than 0. This means that at w equals 2, a minimum exists. So let me just double check something here. Just give me a second here. Just trying to figure out what went wrong with the camera. Okay, there we go. Sorry about that. My camera was not functioning properly. Okay, so let's get back to the question. So we had, we completed the calculation, took the second derivative we ended up with the second derivative is greater than 0, so therefore we have a minimum, and we know we've minimized the cost function, so at the width equal to 2 meters, we know that the minimum exists. So we'll clear the board for a second here. So we know at w equals 2, the minimum exists. We can also calculate, so we're actually here asked to find the cost of the material for the cheapest such container. So all we really need to do now is just plug it in back to the original equation. So at c equals to 2. So let me rewrite the cost function that we originally defined. So here we would have 9w squared plus 144 divided by w. So we'll substitute at c equal to 2. We have 2 squared plus 144 divided by 2. So we get 9 times 4, which is 36, plus 144 divided by 2, which is 72. And 36 plus 72 gives us 108. So here we have dollars. So the minimum cost would be $108. We can also figure out what the other lengths are, but here we're not really asked for the other lengths. We're only really asked for finding the cost of the material for the cheapest container. So this is the final answer for the question. So the solution provided by the junior tutor is incomplete because there is missing values, so I'll mark this as incomplete solution. Answer is the minimum cost that can be obtained is $108. And we'll mark this as incorrect.